My name is Joo-Young Hwang from Samsung Electronics. I want to talk about F2FS, which is a new file system for flash storage. Content like this, I will focus on the design features of the F2FS and present evaluation results in mobile and server benchmarks. First of all, SSD and mobile flash storage is growing interest in an industry because it has many good features, but it also has a negative feature because the flash storage should need erase before write. So SSD drive has internal flash software like FTL that has management role to have to control the erase before write characteristic of NAND flash. So the problem is the random write is bad to flash storage device because it causes a free space fragmentation. So when the free space is fragmented, then the FTL should do a costly garbage collection that causes a sustained random write performance degradation and lifetime reduction as well. So how about using the sequential write-oriented file system for the flash storage? We can think of it because it is generating only sequential write. But we have to think about also the sequential write needs cleaning in the file system layer. So in this paper, we show the design and implementation of a new file system to fully leverage and optimize for the NAND flash storage with block interface. So in this talk, I'm not talking about the NAND flash file system, but the F2FS works on the block interface flash devices. And I will show the performance comparison with Linux file systems. Okay. These 5 are the key features of F2FS. First of all, we have a flash-friendly on-disk layout, and we have a cost-effective index structure. To reduce the cost of cleaning, we have a multi-header logging and adaptive logging feature. And also, to accelerate the Fsync operation in mobile system or server system, we have a roll-forward recovery method. I'll talk about those features one by one. In flash-friendly on-disk layout considers the flash awareness and to control the data location in the device to exploit the parallelism and also the locality. So firstly, we locate the file system superblock data in front of the device to get the locality advantage. So some kind of a device can have a special optimization for locally accessed data. And second one is we have the zone concept and section. These are building blocks of this F2FS file system structure. First of all, we have a 4K byte size block, and segment size is 2 megabyte. And section consists of multiple segments, and we compose zone by clustering several sections together. So I'll talk about the zone and section in the following slides. And also, we have a multiple head logging to separate the hot and cold data. So LFS index structure, I will revisit the LFS index structure to compare it with the F2FS index structure. First of all, it has a superblock and checkpoint, and it has an inode map structure, and inode directory, file data, and all the pointer blocks are linked like this. These constitute a hierarchy of indirection. So when we have to update the file data, even one block, when even one block is updated, we have to update the intermediate blocks, which is required to refer to the new data. So these update propagation is a problem of this log structures, index structure. And the LFS has one big log, so everything goes to the same big log. In contrast to LFS structure, we have a different node mechanism to translate node blocks to a physical address of those node blocks. So you can think of the F2FS node address translation scheme as an extension of IMAP of LFS to refer to the indirect nodes and direct nodes. So F2FS inode has node number for the indirect node and direct node, but it doesn't have a physical block address for those node blocks. Instead, we keep the physical block address of the node in NAT, called node address table. So if we update the file data, we update the direct node because direct node should have a file data block address. And then we update the NAT because that NAT should refer to the new direct node. So that's it. We don't update inode or indirect node because it doesn't have a physical block address of the nodes. And we have a multiple log. Currently, we have 6 log. I will talk about that in more detail in the following slides. Okay. So we, based on the data temperature, we classified the node and data into this kind of levels. First of all, we separate node and data because node has more update frequency than data. And in the node, we separate hot and warm and cold nodes like this. And direct node is more frequently updated compared to the indirect node. And for data, we manage the directory entry blocks as hot data. Some kind of user data can be specified by user as a cold data, or we can use file extension to identify the type of data which is very cold. And we also have a separation mechanism for the multi-head logs. If we have a multiple log, but FTL mapping doesn't know about it, so even F2FS separate the data temperature, but all those logs can be mixed together in one erase block in the FTL. So in case of this zone blind allocation, all the node block and data block are mixed together in the erase block if they are allocated in the same zone. I'm assuming here FTL has a zone-based mapping. In this case, if we separate the log in the different zone, then each node and data log can be assigned to a different erase blocks in the FTL. Okay. So, and we also have a multi-stream interface, which is recently being researched. So in that case, if we have a page mapping FTL, we can specify multi-stream for the multi-logs. So we can separate them, separate each node to the separate stream. Okay, I'll talk about the cleaning procedure a little bit. We have, first of all, we need to select a victim section. The garbage collection is done in a section of unit. And that is aligned with the FTL's GC unit because if the unit of garbage collection in the file system layer and flash translation layer is different, then it would be a problem for FTL because even though the file system cleans some kind of data, but some kind of data is still remaining in FTL erase blocks. So that should be aligned together to have a perfect cooperation. So the section unit should be carefully chosen to match that size. And after victim selection, we have to check the valid block in a chosen section. And also, we have to move valid blocks, and we have to update the cross-reference. And we mark victim section as pre-free. The pre-free section will be freed after the next checkpoint is made. So these are cleaning procedure steps. And as you can see, the cleaning procedure takes much more time if the file system utilization goes high and the volume is highly fragmented. So that is the problem of log structured file system style. So we propose using adaptive logging to reduce the cleaning condition. So the key thing is we have a dynamic write policy. If we have a lower than 5% of a free section in the file system, we switch the write policy to the threaded logging. The threaded logging means we log to invalid blocks in a dirty segment. So we don't have to run cleaning to logging. So but it causes a random rise because the third segment has a sparse free spaces, but it still has a better performance compared to the other file systems. I will show the evaluation result in the following slides. We have to notice that the node is always written with append logging policy here. So the write amplification factor, which is defined as the ratio of actual written data according to versus the user data, may goes high, but the write amplification factor is restrained and kept low as much as possible by using the adaptive logging. And I will talk a little bit about the recovery scheme of F2FS. It has a checkpoint and rollback scheme. We have a checkpoint area which has a shadow copy. As you can see, the yellow blocks are two shadow copies of checkpoint. Checkpoint has a NAT and SIT journaling spaces, which journals updates to the NAT and SIT blocks. So by using them, we can avoid the update to the NAT and SIT structure. And also we have NAT and SIT shadow copies, so the latest checkpoint refers to the latest NAT and SIT blocks. The bitmap refers to the valid copy of them. So the rollback scheme use the checkpoint, the latest checkpoint, to recover the state. And then we apply a roll forward mechanism to recover the Fsync data. So I will talk about the Fsync later in this slide. So to reduce the Fsync overhead, we use a different mechanism rather than checkpoint. So checkpoint is very costly. So we don't do a checkpoint on Fsync. Rather, we update direct node block and data blocks. And the direct node blocks will be written with the Fsync mark. In the roll forward recovery procedure, we recover the Fsync data by searching for the direct node blocks, which has Fsync mark. So first of all, we start from searching the marked direct node blocks, and then per each marked node block, we identify the old and new data blocks by checking the difference between the current version and previous version. And then we update the metadata of F2FS accordingly. And we finally replay the new data block writes. So if all those are done, we create checkpoint. So checkpoint is avoided in Fsync handling, so it gives a higher performance in benchmarks. So let's move on to the evaluation section. We use a mobile system and server system experimental setup, and we ran 8 benchmarks. The iozone and benchmark has a micro benchmark. We run a sequential random read-write performance test, and others are using Fsync very much. And server system has 4 different benchmarks, and video server is mostly sequential, and file server writes many large files with random writes, and varmail and OLTP has a small and large file Fsync behavior. So in case of mobile, F2FS has more than 90% of writes, sequential writes. That gives a better performance in random write case. It is about 3 times over ext4. And in SQLite test case, we have 46% less writes per Fsync over ext4. So that gives nearly 2 times performance gain over ext4. And also Mobigen. Mobigen is testing the Twitter and Facebook app performance, and that shows the similar performance gain of F2FS. So one thing to note about ButterFS and NearFS too, that they perform poorer than ext4 because ButterFS have heavy indexing overhead, and NearFS too has a periodic data flush mechanism. And server benchmark, the performance gain of F2FS is slightly more in case of SATA SSD than PCIe SSD because PCIe SSD has a better performance than a SATA SSD. So the overall I/O performance gain does not contribute to overall performance benchmark score, not so much. And one more thing to note is disk card size matters in SATA SSD because it has a lower interface speed. So the F2FS has more than 2 megabyte size disk card in most cases. But if we change the disk card size to 256 kilobyte, then the performance is degraded by 18% compared to its original performance. And here also the varmail and OLTP benchmark score shows the Fsync performance advantage of F2FS. And if we're using PCIe SSD, the performance gain of varmail and OLTP still exists. Okay, so from now on, I will talk about some kind of in-depth analysis of F2FS design features. First of all, multi-head logging has a better hot and cold data separation scheme. If we use 2 or 4 logs rather than 6 logs, then the data separation doesn't work properly. This diagram shows the valid block portion. So ideally, data blocks should be either full or empty. So in this spectrum, the data should be at each end of the spectrum. But in this case, the red bar shows the data distribution range of 2 log, and the blue bar shows the range of 6 logs data distribution. So you can see that 6 logs gives a better data separation here compared to 2 or 4 logs. Okay, And the cleaning cost analysis, we did some kind of synthetic benchmarks to analyze the cleaning cost. If we use adaptive logging, then we just do node segment cleaning, and we avoid data segment cleaning here. So, as you can see, if the utilization goes high, the performance will be degraded because the adaptive logging causes random writes to device, but write amplification factor doesn't increase much. It is about 1.025 in even 97.5% utilization. And, okay. So the adaptive logging performance is better than other file system in very extreme case. In a highly aged environment, we tested the iozone test on eMMC with a 100% utilization. That means we are overriding data after filling up all the file system volume. So if you don't use the adaptive logging, the performance goes much lower than ext4 case. But when you use this adaptive logging, the performance is similar to ext4 in sustained state. And for SATA SSD test, the performance is better than ext4 case, and the adaptive logging gives a performance gain over F2FS normal cases. Okay, I will conclude this talk. I reviewed the 5 key F2FS features, and I show the performance gain over other Linux file system. It is about 3 times and 2 times speed over ext4 in mobile benchmarks, and more than 2 times in SATA SSD for server system benchmarks. And F2FS is public file system. It's included in the Linux mainline kernel since Linux 3.8 2 years ago. So yeah, it's pretty young still, and we have a growing interest in this file system, and we have exciting features we are working on now. Okay, we have poster tonight, and I'll be happy to take your questions.
Hello, Joris Wilsdell. How does the FTL, when you map your sections to the FTL section, how does the FTL know that you're doing that? You're just writing to an LBA as far as it's concerned. It doesn't know that what you're trying to, I mean.
Mm-hmm. So F2FS can configure the section size according to the FTL's characteristic. So the file system configurator should know the FTL characteristic beforehand. So that's the.
Well, what I meant is, I mean, so do you write the whole section at once and don't intermix any other writes? Is that what you're doing? I mean, if you're writing to 6 logs, you could be writing 1 to 1, a little bit to 1, all 6. It sees 6 independent writes. It doesn't know that you're actually writing to 6 independent sections, and that you would like it to spread it out that way.
Mm-hmm. So yeah, I talked about zone-based mapping there. Zone-based mapping has some kind of LBA zone that has an erase block for those zones. So each zone has a different erase block concurrently. So if they are matched together with F2FS, they can go together concurrently. But in page mapping FTL, all those 6 rows can go mixed together in one erase block. That is a problem. So you can think of a multi-stream interface that has manual instruction to the device to match each log to one stream of internal FTL stream. So you have to use that kind of interface to control that behavior.
I think this is related. What's the other way to rephrase that question is, what is the API you need from the flash translation layer, like the multiple write points I've heard described, but you don't actually control whether the where level layer is going to honor those zones, right? So I'm curious, have you talked with SSD manufacturers? Have you gotten them to give you a useful interface yet?
Yeah. Actually, Samsung has published one paper about multi-stream interface in previous hot storage conference, and it is a kind of a interface to aid the file system designer to control their behavior to match with the FTL devices.
Okay, thanks.
Thank you.